This is video 7C, and we are coming right off of video 7B, where you learned that frequency equals the speed of light divided by the wavelength of the light. So now we're going to do a couple examples that manipulate that equation that you have memorized. Okay, so example 7.2 is where we're starting, and this is on page 217. Example 2 says, a violet light wave has a wavelength of 405 nanometers. What is its frequency? And then it gives us the speed of light there, and it also tells us what nano means. Okay, so in example 7.2, we are looking to find frequency, and what we know is that frequency equals C over lambda. C is 3.0 times 10 to the 8th meters per second. That's the speed of light. Lambda equals, tells us in the problem, 405 nanometers. Okay, so I just have to divide them. However, I do see one little issue. I see that my units are not going to measure up. So I am going to convert nanometers into meters. So I'm going to start with that. 405 nanometers times, we want nanometers to be on the bottom so that those units cancel each other out. And we want meters to be on the top because we are trying to get into meters. Okay? Now I plug in my numbers. I know that 1 nanometer is 10 to the negative 9th meters, okay? In the problem, I paused because in the problem it said, yes, it gave us the prefix. Nano means 10 to the negative 9th, okay? So if I plug that into my calculator, I will get 4.05 times 10 to the negative 7th meters. Yes, that is correct. Okay, and now that I have my wavelength, this is wavelength. So now that I have my wavelength in meters, I can now plug my two numbers into the equation that I know, which is frequency equals C over lambda. C is 3.0 times 10 to the 8th meters per second. My lambda is 4.05 times 10 to the negative 7th meters. Now looking at this, I can see that my 2 meters are going to cancel each other out. So I'm going to end up with these weird units of 1 per second. But if you remember, 1 per second means hertz, which is how we measure frequency, okay? So I'm going to end up with, I'm just going to write 1 per second or hertz. That's going to be the unit that I end up in, okay? If I plug this into my calculator, and I'm going to show you how to do that just to refresh our memories. We do 3.0, and then we would do that E button, and then we would do 8, okay? Divided by 4.05, E, 7, but then we have to also press the plus or minus to make it to the negative 7th, equals, okay? So this is what we would plug into our calculator. I'll put this in these red brackets like that. Okay, so after I plug that into my handy dandy calculator or phone, I would end up with an answer of 7.4 times 10 to the 14th power 1 per second or hertz. So that's how many times that the wavelength is hitting a given point per second. That's a lot, isn't it? So that's a pretty high frequency, okay? So we solved for frequency there. Let's do the next problem in example 7.2 also. A light wave has a frequency of 4.7 times 10 to the 14th hertz. What is its wavelength and color according to the chart in figure 7.8? Figure 7.8 is the visible spectrum chart, Roy G. Biv. So we're going to solve for wavelength. We're going to figure out what the wavelength is, and then we're going to look at the chart and see what color that particular wavelength is, okay? Let's erase this a minute. Always letting my markers roll off the table. Erase, erase, erase. Okay. Marker. Black marker it is. All right, we are still in example 7.2. This is the second one. Find, what are we looking for this time? We're looking for wavelength. Wavelength, like that. Okay, we know that frequency equals C over wavelength, or C over lambda. And so if we rearrange that using our algebra skills, we would know that wavelength, to solve for wavelength, would be C over F. So that's what we're going to be doing this time, okay? We know C equals 3.0 times 10 to the 8th meters per second. That's how fast light moves. And we know that the frequency is, got to look back to our problem, 4.70 times 10 to the 14th hertz, or 1 per second, okay? So that's how many times the crests are hitting a certain point. That's what frequency is. All right, let's solve for wavelength. I was just checking my units, but my units are okay because I'm in meters per second, and then I'm in hertz, which is per second. So my units are gonna match up and be able to, something's going to be able to cancel out. The seconds are going to cancel out so that my units will end up in meters. Okay, so lambda equals C over F, which is 3.0 times 10 to the 8th meters per second, divided by 4.70 times 10 to the 14th, 1 per second. Okay, so my seconds are going to cancel each other out. And I'm going to end up with an answer of, I'll fast forward to the answer. You guys should put it into your calculator to make sure that you know how to put it in your calculator and get the right answer. 6.4, we can only have 2 significant figures because C only has 2 significant figures. Okay, 6.4 times 10 to the -7th meters. Okay? Now, we were also supposed to be able to match this up on the visible spectrum to tell what color this light is based on its wavelength, okay? But the visible spectrum shows us wavelengths in nanometers. So now we need to convert this to nanometers. So 6.4 times 10 to the -7th meters, and I'm going to multiply it by my conversion factor with meters on the bottom this time because I want meters to cancel out. Nanometers on the top. I know that 1 nanometer is equal to 10 to the -9th meters. Okay? So my answer would come out to be 640 nanometers. How many significant figures is that? 640. That's right, 2. Because the 0 here is not a significant figure. Just the 6 and the 4 are, okay? So my wavelength is 640 nanometers. I'm going to look back to figure 7.8, and I see that 640 nanometers would be orange. Pretty cool. Orange is the second part of the answer. And that's how you manipulate the equation F equals C over lambda. Okay, one more thing I want to add in video 7C. Here I have drawn out, again, the visible spectrum, not again, for the first time. It's also in figure 7.8. So pretend this is the visible spectrum with all the different wavelengths, okay? And I don't have the exact numbers here, but you can refer to the figure to see what I'm talking about. And then of course, these are the different colors, red all the way over to violet. Now you need to know that on the visible spectrum, the red side is for larger wavelengths. As wavelengths get smaller, you move this way on the visible spectrum. So that violet has the small wavelengths, red has the largest wavelengths. I believe I have told you this before. And then for frequency, these are smaller frequencies. These are the large frequencies, okay? So when lambda is large, frequency is small. When lambda or wavelength is small, frequency is large. They are called inversely proportional. Okay, you say something is proportional when like both get higher or lower together. I shouldn't go like this because it looks like I'm doing a wavelength. Anyway, if you say that two values, one gets big, the other gets big, one gets small, the other gets small, those are proportional to each other. But when you say that as one gets large, like wavelength, the other gets smaller, like frequency, that's called inversely proportional. Okay? I believe that's all I wanted to tell you on that. So know that large wavelength and small frequency go with red. Small wavelength and large frequency go with violet. And you can kind of imagine why they are inversely proportional. Because if this is a wavelength, let's say that this wavelength is relatively large, okay, the waves are not that close together. So frequency is going to be kind of small. You're only getting hit with a wave. Let's imagine we're standing on a beach. You're getting hit by the wave maybe 1 per second, okay? If you have a wave on a beach that looks like this, or waves on a beach that looks like this, your wavelength is a lot smaller, but you're getting hit with a lot more waves per second. So the frequency that you're getting hit with the waves is a lot bigger, okay? So I hope this makes sense in your minds. The two, wavelength and frequency, are what we call inversely